Okay, so our next topic is surface integrals, right? So the idea is we have some function defined in all of space. So, right, so say W is just a function of x, y, and z. Right? And whatever quantity this represents, we want to essentially add them all up, add up all the quantities on the surface S. Right? So I have a surface, each point here will have a different value of, say, W, right? So think of this as your scalar field, and we're just adding up all those values along the surface, right? So we get a surface integral over the surface S of this quantity here, right, ds. Right. To bring this a little more down to earth, imagine if this function f was just the density function, right? Each point has a different density. I'll use rho instead of sigma, either way. So what are we doing then when we're adding up all the little densities at each point? We're adding up the density. Oh, this is surface density, right? So I really should use sigma here because it's not volume, it's surface density. Right? So this is the mass per unit area, right, at each point. So when you add those up, right, you get the mass of the surface. How much does this surface weigh? Well, what is its mass anyways? Right? It's the weight divided by g, of course. Anyways, yeah. So yeah, if f is some other quantity, then you're just adding up all those little quantities over the entire surface. Okay, so think of your f as like a density function. Right? It varies. The density could vary over the entire surface here. And when you add up all the density times the areas, right? So sigma times ds is now a mass. You can think of that as your dm, right? Your little piece of mass on this little patch of the surface here. And so, yep, when you add up all the little masses over the entire surface, you get the total mass of the entire surface, right? Over that, at least over that region R. Okay, so that's the idea of a surface integral, right? Okay, so as a practical matter, how do we calculate these? Okay, so it depends on how your surface is defined, right? Suppose our surface is defined, S is defined the old-fashioned way, Z as a function of x and y. Right? Notice I'm not using f. Why? Because then that would be horribly confusing, because this f here is not the same as this f here. Right? Remember, this f is like the density. Right? Here we're just defining the surface, irrespective of the density. Right? So this is just some surface. So I'm going to use g instead of f. Okay. So if it's defined as a function of x and y, the usual way, right? So you have the xy plane sitting below it, and then z is the height above it, right? Then your ds is going to be calculated as the square root of, well, 1 plus the partial of g with respect to x squared, plus the partial, right, it's a function of x and y, of course, right, plus the partial of g with respect to y squared. Right, so that should look familiar. Right, this is something we did in 14.5 when we talked about surface area. Right, the surface area is just the integral over ds, right? Oh yeah, don't forget the dA here, right? The dx dy. So yeah, this is what we did in chapter 14 when we wanted to find the surface area of a surface given as a function of two variables, right? So yeah, now if you want the surface integral, like let's say we want to calculate the mass, right? So now we have to calculate this as the integral, the double integral over S, over the surface S, of the function f, right, times the square root of 1 plus, right, gx squared plus gy squared, I'm running out of space, right, times dA, which is, let's say it's right dy dx, or dx dy, depending on vertically or horizontally simple region, right? Okay, right. So that's nothing new. That's just like surface area. But now if you want the mass, then you integrate the density function. Think of that as the density function over the surface, right? Oops. Okay. All right. But what if your surface is given parametrically? Okay. So now suppose S is defined. It's an S. Is defined parametrically, right? R as a function of u and v is just the usual, right? X of u and v, y of u and v, and z also a function of u and v. And then, u and v range over some interval here. Yep, say u is between a and b and v is between c and d. Right, so that defines the region R of the UV plane. Okay, so in that case, your ds is going to be a little bit different. It's going to be the magnitude of the partial of R with respect to U, cross product with the partial of R with respect to V, right? du dv, which is our dA here, right? Or again, and I haven't written it this way yet, but if this helps, you can write it in the longhand notation, partial of R with respect to U, cross product partial of R with respect to V. And then don't forget to take the magnitude of that, right? Because this is an area, it's not a vector, so it's a number, magnitude. Oh, it's a function of U and V in general. If you're lucky, it just works out to be a number, but usually not, right? Okay, so that's the idea here, right? So to do a surface integral then, surface integral over the surface S of some function, f of x, y, and z, right, with respect to S. So as a practical matter, if the surface is given parametrically, this is the region R of the UV plane now, and you still have your function f, but then you have to multiply that by the magnitude of RU cross RV, right, with respect to U, with respect to V. All right, let's just do an example. Okay, so we want to evaluate this surface integral, right? We're going to do the surface integral of x times z over the surface S. S is just the plane, 3x plus 4y minus z equals 12, right? Over the, right, so that's an infinite plane, obviously, right? It's very possible that we'd get like an infinite surface area. So we're restricting it to the rectangle, the region R, is just where x is between 0 and 2 and y is between 0 and 5. So 1, 2, right? 1, 2, 3, 4, 5. And that's R, right? So that's just the usual xy plane. All right, so yeah, there's a plane sitting above it, right? So in 3 dimensions, right, here's your rectangle, R, and then you have some plane sitting above that rectangle, right? Boy, that's an awful looking plane. Let's try that again. So that's a little better. Right, so we're only looking above the rectangle here, right? So maybe this piece of it. Okay, right, and we're not asking for the area of that piece, we're asking for the surface integral, right? So we're integrating some function, and in this case, our function, f of x, y, and z, is just x times z, right? So that's what we're evaluating. So, right, think of that as your density. The density is just x times z. So we're getting the mass, then, of this piece of the surface, this piece of the plane. Make sense? Okay. All right, so where do we start? Well, our surface, right, S, is the plane, right? it's not given parametrically, but we can write it parametrically if you want. I would just solve for z here, right? Z is just going to be 3x plus 4y minus 12. Yeah, okay, fair enough. You know what? I want to make this positive. So I want to make this negative 12 here, and that makes this a positive 12. It will change the answer, of course, but yeah. So make that a plus 12. Okay. Yeah. Or better yet, the equation should have been 3x plus 4y minus z plus 12 equals 0, right? Because usually that number's on the left with the other numbers. Plus 12 equals 0. All right. Okay, so that's my surface. That's my plane. That's my g of x, y, right? So z as a function of x and y is g of x and y. Okay. Right, so to get the ds, remember we have to take the square root of 1 plus the partial of g with respect to x squared plus the partial of g with respect to y squared. And that's going to be the square root of 1 plus 3 squared plus 4 squared. So if it weren't for that 1, we would get a nice answer. We would get 5. Unfortunately, we don't. We get the square root of 26, right? Oops, times dA. There's a dA in here too, right? Yep. Right, so that's my ds. Right. And what's x times z? What's the function we're integrating here? It's x times z, but right, this is going to be, right, dA will just be dy dx. There's no z. So we have to rewrite z in terms of x and y, and that's just the usual, right? 3x plus 4y plus 12. That was how it was defined. So, right, we're really going to integrate 3x squared plus 4xy plus 12x. Right, so this is our function of x, y, and of course it doesn't depend on z now, but it does depend on x and y. All right, so put it all together. We want to do the surface integral of xz over ds. So that's going to be the integral of xz. We rewrote as this function here. So this is going to be 3x squared plus 4xy plus 12x. All times ds, but ds is the square root of 26, right, times dy dx. And again, we'll do vertically simple region here. It could be either vertically or horizontally. Y goes from 0 to 5, and x goes from 0 to 2. Again, that was given, right? That was the region, the rectangle, underneath the plane. All right, so this, again, is a pretty standard double integral we did in chapter 14. Square root of 26, that's a common factor that can come outside. Let's do the inside integral first. With respect to x, we're going to get x cubed plus 2x squared y plus 6x squared, right? Yeah. Oh, that was with respect to x. Oops. We're doing y first, aren't we? Okay, let's do it again. 3x squared y plus 2xy squared plus 12xy. Evaluated between y equals 0 and y equals 5. So now we just plug in y equals 5 here. When you plug in y equals 0, you usually get 0, right? All right, so 3 times 5 is 15, so 15x squared. And then 5 squared is 25. 25 times 2 is 50, so 50x. And then plus 12 times 5x is 60x. Okay, and well, 50x plus 60x is 110x. Almost not necessary, but let's make that official. Right. Okay. Yeah, now we just integrate with respect to x. And that's going to be 15 divided by 3, oops, sorry, times, not equals, is 5x cubed, right? Plus 110 over 2 is, well, 55x squared. And x varies between 0 and 2. So again, when you plug in 0, you get 0. So this is square root of 26 times 5 times 2 cubed plus 55 times 2 squared. And I'm trying to do this all in my head. Let's see. 5 times 8 is 40. And then 55 times 4 is 220. So square root of 26 times 260. Sounds good to me. Again, unless I made a silly arithmetic mistake, which I very well could have, I think that's it. Right? So again, what does this number represent? It's not the area, right? I mean, look at the area of the rectangle here is only 10, right? 2 times 5 is 10, and this is way bigger than 10, so I don't think that's the area, right? That's the mass. Remember, the density varied with x and z. So, right, so we're getting the mass of this portion of the plane given this density here, right? All right, so that's it for this example. That's our evaluating a surface integral of a function over the surface. All right, maybe we should do one more. So this is the surface integral of the quantity xy over z, right? So that's our function now. It's a function of x, y, and z. So x times y, but divided by z, right? Over the surface S, right? What is S? S is the surface, z equals x squared plus y squared. And we saw that in the previous video. That's just your paraboloid, right? Yep, so x, y, and z, right? Or actually it's the portion of the paraboloid over the region of the surface, right, over the region of the xy plane. Notice that x squared plus y squared, which is r squared, is between 4 and 16. So r is between 2 and 4. So 1, 2, 3, 4. I think that's about right. We're talking about this region in here, right? Outside of the circle of radius 2, but inside the circle of the radius 4. It's a little lopsided, but you get the idea here, right? Yeah, so let's highlight that region. Oops. Yep. Oh, okay. Fair enough. So it's between, yes. Oh, I shouldn't even try to trace around the outer circle of radius 4, right? Okay, yep, so this is r equals 4, right, and this is r equals 2. Right. So you can imagine what piece of the paraboloid you're getting here, right? You're getting, say, just this piece of it up here, right? Right, so what's below is erased. So it's almost cylindrical at this point, right? Or just, just think of a bowl with a hole cut out at the bottom here. Right? I'm exaggerating a little bit, but that's the idea, right? Okay, right? And again, we're not getting the area of this. We're getting the surface integral. Think of this as the density function again. And if that is the density function, then you're getting the total mass by evaluating this surface integral, right? All right. again, z is a function of x and y. But remember, we have to use g now. So g is x squared plus y squared. And what do we need? Right? Remember, for ds, we need the square root of 1 plus gx squared plus gy squared. And I think we've done this before, right? This is the square root of 1 plus 4x squared plus 4y squared, right, times dA. Right? So you can see where this is going, right? Because of the radial symmetry here, we're probably going to switch to polar coordinates, in which case dA is now r dr d theta, right? Remember, it used to be dy dx, but now we need an r dr d theta, right? So that's the ds. And yeah, so the function we're integrating here, the f is, x, y, and z, right, is x times y divided by z. But remember, we have to write z in terms of x and y. So that's just x squared plus y squared. But if we're switching to polar coordinates, we need r and theta instead. So x is r cosine theta, y is r sine theta, and x squared plus y squared is just r squared. So notice we have a very happy coincidence here. The r squareds end up canceling. And what we're integrating here, the f, if you will, in terms of r and theta, is just cosine times sine, or maybe I'll write it the other way, sine times cosine of theta. All right, so putting this all together, we can now do the surface integral of the function ds. Right? It's going to be, the function is just sine theta cosine theta, right? And the ds, right, so this is my f of x, y, and z. And then the ds is the square root of 1 plus, 4r squared times r dr d theta. Right. And let's, I'm running out of space here. Shoot. All right, well, maybe we can do this quickly. R goes from 2 to 4. Right, remember, you're not going from 0 to 4. You're only going from 2 to 4 here. And theta, well, we want to go all the way around, right? So 0 to 2 pi for theta. Right. So I think we can just split this up as the product of the two integrals. The integral from 0 to 2 pi of sine theta cosine theta d theta times the integral from 0 to 4 of the square root of 1 plus 4r squared r dr, right? And the reason why we can do that is because the limits, right, especially the first limit here, doesn't depend on theta. And this is a product of a function of theta times a function of r. So because of that, we have the product here. And let's do the theta integral first, because it comes first, right? So this is just a substitution. U is sine theta. Du is cosine of theta, d theta. So that's my du, u du. But notice, sine of 0 is 0, and sine of 2 pi is 0. So the integral from 0 to 0 is 0. Right? So it almost doesn't matter what this integral is, as long as it converges, right? As long as this is some finite number, say n, right? The first integral is just 0. So 0 times n is 0. Right? So yep, you can work out the second integral, but it doesn't matter what that number is, because we know it's going to be finite. This integral does converge. We've done similar ones before. Right. So if you did work out the r integral first, well, that was a waste of time because the first integral was going to be 0, and then it didn't matter what this is. So, yep, the surface integral here is just 0. Right. Now, what does that mean? Right? Remember, if this is not the surface area, obviously the surface area is not 0. If f is the density function, right? F represents the density so to speak, then the mass is 0. Well, how can the mass be 0? So this is strange here, right? This is a little bit weird. And here's the explanation, right? Z, of course, is going to be positive. Oops, I'm using the wrong color here, right? Because Z, right, x squared plus y squared is going to be greater than or equal to 0. In fact, on the disk here, it's going to be greater than 0. I mean, right, because it's going to be greater than 4, which is certainly bigger than 0. So Z is positive. But notice x and y could be positive or negative, right? So in the first quadrant here, x and y are both positive, so x times y is positive. In the third quadrant, x and y are both negative, but remember you're multiplying x times y, so a negative times a negative is positive. Right? But in the second and fourth quadrant, it's a positive times a negative, right? Or a negative times a positive. So there's a symmetry here, right? Whatever positive answer we get for the first and third quadrant, we get the exact opposite for the second and fourth quadrants. Right? So they end up canceling out. And so that's why we get 0. So yeah, so maybe density is a bad example here because I don't know what negative density means. You know, it means you're missing something, right? So whatever quantity this is, when you add up over the entire surface, right, part of it is positive, part of it is negative, and they cancel in equal parts, right? They're equal parts each. So that's the explanation. That's how you can get 0, right? If the values of this function f can be positive or negative, then you can get either a positive answer or a negative answer, or in this case, they cancel out exactly and you get 0. Right, and that's part of the reason why I wanted this to be plus 12 instead of minus 12, because I knew with the minus 12, I think you were probably going to get a negative answer here, and I wanted to avoid that. So that's why. Anyways, we managed to finish before the end of before I ran out of space. Okay, so we briefly talked about orientation of a surface in the previous section, and so let's make this a little more clear here, right? So first of all, let's just quickly review. We did talk about the orientation of a curve, say C, and all that is whether you're going one way or the other. So if you're going from point A to point B, right, that would be a positive orientation. And if you're going from point B back to point A, going backwards, that would be a negative orientation. Right? So it just matters what direction you're going in, right? Right. And if it's a closed curve, well, then it's just clockwise or counterclockwise, right? So I think we did counterclockwise is the positive orientation, and if we went around clockwise, that was the negative orientation, right? So yeah, for a curve, it's just going one way or the other, right? Reversing directions. As we talked about, the surface is a little more complicated, right? Because it's, what does it mean to go one way or the other? And we alluded to the normal vector, right? The normal vector can either point essentially upward or downward. So that choice of which normal vector you pick, the one that points upward or the one that points in the opposite direction, gives us the orientation, right? So you have the top of the surface or the bottom of the surface, right? If you're talking about a closed surface like a sphere, then top and bottom no longer work because this is the top, this is the bottom. You can just move the vector continuously this way, and it's the same side of the surface, right? So we don't say top and bottom anymore, we say outward and inward. So this is the outward normal vector n. Or if you want the negative orientation, you can just go inside the sphere And these are vectors pointing inward. So that would be the inward normal vector, which would be negative n, right? Right. So that's the opposite orientation, right? And to make matters worse, there are some surfaces that don't have an orientation. In other words, they don't have two sides, right? They don't have an inside and an outside. They don't have a top surface and a bottom surface. It's all one side. And the example of a good example of this is the Mobius strip. Right? So you take a strip of paper like this, right? And if you fold it in on itself like this, take this side over here, the left side, and connect it to the right side, you can do that one of two ways, right? If you keep it the same, all you get is this little ring or cylinder. It's a short cylinder here, right? But if you twist this, you get, and I can't draw it, you have to do it yourself, right? Twist this halfway around and then connect the two surfaces. What you'll see is that you don't have two sides anymore. You just have one side, a one-sided surface, right? So this has two sides. This has the outward and then the inward. Yep, outward and inward. But the Mobius strip, right, only has one side. It's all one side. So there's no orientation because we can't pick one of two vectors. There is no n and negative n. There's just n, right? Right. So, or instead of saying no orientation, we can just say it's one orientation. It's one-sided. Effectively, it's what's called non-orientable. It's a non-oriented surface. Right. So that Mobius strip is an example of a non-oriented surface. Another example is the Klein bottle, and I definitely can't draw that because this is a four-dimensional surface, or four-dimensional? No, three-dimensional surface. It's a three-dimensional surface, 3D surface, right, sitting in four dimensions. It's embedded in four dimensions. And I can't draw four dimensions, so we're not going to be able to draw the Klein bottle. Right. There's a way around it if you can, if the Klein bottle essentially intersects itself. If it crosses itself, you can, look it up online and you can see the example of that. So we're done with that, right? All our surfaces will have an orientation from this point on. So don't worry about the Mobius strip or the Klein bottle. Those are essentially bad examples. Okay, now we come to the idea of a flux integral. Oops, sorry about that. Flux integral. So what is flux, right? Flux is essentially the amount of something flowing through a surface, right? And I know that's very vague. So here's an example, right? Suppose we have a river running, let's say, to the right here. So this is just water flowing to the right at a certain speed, right? And in various directions, of course, right? And you take let's say you take a fishing net and you stick it into the water here. So here's my fishing net. Let's say there's no net, right? It's just a loop, right? And you put it inside the water here, right? And you can measure how much water flows through the loop, right? In a given amount of time, let's say per second, right? Each second. So you measure this much water, right? Flowed through the loop in 1 second, right? That volume of water then is the flux. Okay? So the flux is the amount of something flowing through a particular surface. In this case, the surface is just the disk here. It's the hoop, right? It's just the disk. Let's say it's circular, right? So, yeah, so whatever's flowing through that surface in a given amount of time is called the flux. And I know that's still vague, but that's the idea, right? Of course, if I turned my loop sideways like this, then water's flowing across it, but not through it. So by turning the loop in a specific direction like this, I can get the flux to be 0 because no water's flowing through it. It's just flowing over it or around it, but not through it like this, right? Yeah, right. Or if I turn it around, this way, and now the water's flowing the other way, right? Or, well, okay, yeah. So it's still flowing in this direction, but since I turned it around, the vector's pointing the other way, so now I get a negative flux, right? So, right. And so, yeah, it depends on the orientation, right? If the normal vector is pointing this way, right, and the water is also flowing this way, then it's a positive flux, right? But by turning the loop around, you switch the orientation, right? Now the normal vector points this way, and if the water is still flowing this way, you get a negative flux, right? So flux can be positive, negative, or 0. Right. And again, I'm using water as just an example of, well, of a vector field, right? At each point in the river, the water has a certain velocity and a certain direction, generally all pointing to the right, although, you know, when you get to a bend in the river, then the water turns, and the water might be flowing in a different direction at a different speed, and so on. Okay, but yeah, we're not going to study fluid dynamics here. This is just the very basics of, you know, of water as an example of a vector field. Oops, vector field, right? So capital F for our vector field, right? But we can also find the flux of, say, the gravitational field or the electric field. I'm just being very sloppy here. There we go, vector field. I'm trying to spell F-I-E-L-D. Okay. Yeah, so the electric field, the magnetic field, right, the gravitational field, we can take the flux of those. Even though nothing's really flowing, when you see a vector field, like say an electric field, I mean, first of all, you can't even see it, but there's nothing really flowing. It's just these imaginary arrows in space, right? So yeah, but you know, if you have a surface like a loop, you can measure all the electric field vectors through that loop, and when you add them all up, you get the flux, right? So it's the process of adding them all up is why we need to do an integral here, right? So here's the example of a flux integral. We're doing the integral over the surface, in this case, just the loop here, right? Or the disk inside the loop of a vector field, right? And we're going to take the dot product with the normal vector. I'm going to use capital N, the normal vector to the surface. So, all right, so I regret using little n for my normal vector. We should be using capital N now for our normal vectors. Yeah, I think there's a reason why I'm using capital N here. Little n could be any normal vector. But this capital N, right, has to be a unit normal vector. It has to have magnitude 1. Okay, and the reason is because we're just looking for the flux of F, the vector field. We don't care the magnitude of n. We want that to be 1. Right? Because if n is, let's say, has a magnitude 5, then we're multiplying the vector field times 5, which means we're getting 5 times the flux, if that makes sense, right? So yeah, capital N should be a unit normal vector, right? So the magnitude of capital N has to be 1. Up until now, our normal vectors were generally not unit vectors, usually not, right? But now we're forcing it to be 1. So that's the difference between capital N and little n. Right, so how do we evaluate these flux integrals as a practical matter, right? So an example, they give you a surface and they give you a vector field, evaluate the flux integral, right? So we'll get to those, but we need a way to do that, right? Effectively, we need the ds again, and the ds will be the same whether it's a parametrized surface or a surface given as a function of x and y, let's say. Yeah, so first let's assume that S is given, say, Z as a function of x and y. Okay, so, right, so it depends on if n is pointing upward, right, with a positive Z component, then the flux integral of the vector field dot n ds can be calculated as follows. Okay, so it's going to be the double integral over the region R, right? That's the region underneath the surface, right, given by the bounds, of the vector field F, right? Dot product with the vector negative partial of g with respect to x squared. Oh, not squared. I'm sorry, not squared. Right, times I minus the partial of g with respect to y times j plus k. Right, and then dA, which is usually dy dx or dx dy. Right, so this is my n, and this is my, well, ds. Right, or let's put it this way: the whole thing is n ds. Right. Yeah, it's hard to separate the two. Because again, this might not be n. This might not be a unit vector, right? Right. But that's how you can do that. On the other hand, if n has a negative z component, so for n having a negative z component, well, you do almost the same thing. It's the double integral of r over r of the vector field dot product with positive gxi plus gyj, and then minus k, because right, it's going to have a negative z component, right? Yeah, so that's right. So it depends on the orientation of the surface, right? So if this is our surface here, if our normal vector points upward, then we use the first one, the blue one, and if n points downward, right, then we use this one here. So, right. Okay, and generally n will point upward, although not necessarily, right? So we'll just have to be careful of that. It depends on the surface. Right. Now, suppose that S is given parametrically, so as a function r of u and v, right? And that's just the usual x, y, and z. We'll dispense, we know they depend on u and v, right? And this is over a region r of the uv plane, right, with some condition on u and v. Right, here, of course, this will be, r will be a set of points x, y in the xy plane. So I forgot to mention that, but I think we've done that before too, right? So in this case, we can evaluate our flux integral, f dot dn ds, the following way, right? So we're going to integrate over the region R, the vector f, right, dot product, the partial of r with respect to u, cross the partial of r with respect to v, oops, right, no magnitude, right, that's a vector now, because we're taking the dot product of two vectors, right, and this will just be, you know, the dA, which will be, you know, typically du dv, or dv du, right. Okay, right, and again, this might not be a unit vector, but what happened here is the following, right? And this, we can apply the same argument here, that this is not a unit vector, right? So that's not our n. But yeah, so here's what happened. We took the dot product of, R, over the region R. We took the dot product of F, and we can make this a unit vector, right? This is RU cross RV. And to make it a unit vector, we divide by its magnitude. Right? But remember what ds was. ds was the magnitude of RU cross RV times dA. We did that earlier, right, in the last video. So as a fortunate event here that these cancel, and you end up with just this, right? So yeah, so you don't have to remember any of that. In fact, all of these are on your formula sheet, but this is sort of the practical way to calculate these flux integrals. Right, and now all that's left to do is actually do some examples of flux integrals. And flux integrals are essentially just surface integrals, right? But they're surface integrals where you're integrating a flux quantity rather than, say, a density, right? But remember, it is a dot product. It is a scalar function that you're integrating over in the end. Okay. Okay, first example. We have a vector field, F, right? And it's given in its component form, x squared I plus y squared plus 2yj plus yzk. And the surface S is given as z equals 3 minus y squared. And hopefully you remember what this is, right? This is not a paraboloid because there's no x squared, right? In fact, it doesn't depend on x, right? This is a cylinder. Specifically, though, it's not a circular cylinder. It's a parabolic cylinder, right? So again, just think of a cylinder like this, right? So yeah, when you graph it out, it probably looks, something like, I don't know how to describe this, right? Like a mailbox, almost, right? Or maybe an airport hangar or something. I don't know. But it's a parabolic cylinder, okay? So that's the surface, and it's only over this region R, again, defined by x is between -1 and 1, and y is between 0 and 3, right? Oh, so I didn't give you the question, right? So the question, of course, is to evaluate the flux integral over the surface S, right? F dot n ds. And I should warn you, different books have different notations. In particular, I've seen physics books call this quantity dA with a vector over it, which is kind of a funny way to say that area is a vector. So it would write the flux integral as F dot dA. And again, how is area a vector? Well, suppose we have this square here. Like, this is in the xy plane, right? So area can be a vector if you give it a direction. In this case, the normal vector, n, right? So, right, if I multiply the area of this, say A times n, then I have the area vector A. Okay. Again, I don't like thinking of it that way, but there's nothing wrong with it. It's just weird to think of area as having a direction, but when we're talking about the direction of the area, we're talking about the direction of the normal vector to the plane, to the tangent plane, right? Okay. So yeah. So we're not going to do that, right? We're going to use this notation here without the dA. Okay. So how do we evaluate that, right? So, well, our surface S is given as a function of x and y, right? So that's my g of xy. I mean, we could parameterize it, of course, but why bother, since we can do it the way where S is defined as a function of x and y, right? So what else do we need? Notice we need the two partial derivatives. So we can get that very quickly. The partial with respect to x is 0, and the partial with respect to y is -2y, right? So that means my ds is going to be the square root of 1 plus gx squared plus gy squared. However, if we do it this way, The flux integral then will just be the integral over S of the vector field F dot. And now the question is, which orientation do we want? Do we want upwards or downwards? I like upwards, right? So this will be the positive orientation going upwards. So we'll use the negative gxi minus gyj plus k times dA, which could be, let's do dy dx. You can do dx dy because the region is horizontally simple or vertically simple. It's a rectangle. Right? Okay, well, we have the partial derivatives, so now, let's see. X just goes from -1 to 1. Y goes from 0 to 3. And the vector field is, well, x squared 2y, yz, dot product with this vector here. So it's going to be, well, -0 is just 0. Negative 2y is positive 2y. And then 1. And this will be dy dx, right? So we still have to take the dot product. By now you're all experts at that, I'm sure. Right? X squared times 0 is 0. Plus 2y times 2y is 4y squared. And then yz times 1 is plus yz. Okay, so our integrand, the thing we're integrating, is just 4y squared plus yz. Right? But hang on, we're taking the integral is with respect to y and x. There's no z there. So we can't just leave the z as it is. What was z? Z was the surface. It was defined this way. So we have to substitute for z, right, 3 minus y squared. So let's do that now. So it's going to be 4y squared, that part's okay, plus y times z. Z is 3 minus y squared. Right. Now we can do the integral. Right? Now there's no problem here. So we'll do the inside integral first, as always. Although, right, none of this depends on x, so you can split it up as the product, but let's do it the usual way here. So what do we get? We're going to get, well, 3y plus 4y squared minus y cubed. So to integrate that, we're going to get 3 over 2y squared plus 4 over 3y cubed minus 1 over 4 y to the fourth. Evaluated between 0 and 3. We need some more space here. And then we still have one more integral to do, but that will be the easy one. So what happens when we plug in 3 here? We're going to get 3 times 3 squared, so that'll be 27 over 2, plus 4 times 3 cubed over 3, 27 over 3 is 9. 9 times 4 is 36, I hope. And then 3 to the fourth is 81 over 4. So this is just a constant we're integrating here. We can take that constant outside. And that constant is, 117 over 4. Oh, right, 1 dx. 117 over 4. That'll come outside. Right? And then, when you do the integral, you'll just get 2. Right? It's 1 minus -1, which is 2. Oops. That 2 should have been a 4. Because when you multiply by 2, it'll end up being a 2. Yep. So 117 over 4 times 2 is 117 over 2. Or, if you prefer, 58.5. Okay, so that's the flux integral. What does this number represent physically? Well, okay, so we have our parabolic cylinder here. Let me maybe make it a little bigger here. So here's the parabola, and then here's the cylinder part, right? Right. Right. And again, this is over the rectangle R, the region R here. No, it doesn't include the bottom, right? So this is not a closed surface, right? We're not including the bottom of the cylinder here, right? So this is an open surface, right? And we have a vector field everywhere in space, right? So we have vectors way out over here, but we're only really concerned with the vectors that are attached to the surface. So this vector, right? This vector, and so on. And again, this is not an actual graphic representation of the vector field. I'm just drawing some generic vector field here. Right? Okay. So you get the idea, right? There's a vector field pointing everywhere along the surface, right? So let's just take a small piece of that surface, say this little piece right here. I'm trying to make that a square part here. Obviously, it is curved a little bit. So yeah, let's blow it up and make it a big piece here. Right. But over that small piece, the vector field will not vary significantly. I mean, I drew it in a very random way here, but the vector field will not change all that much. Right. And if you make this even smaller, then of course there's basically just one vector over that surface here. And you take the dot product of that with the normal vector. Let's say this is the normal vector n, right? Unit vector. And that's a measure of the flux through that little tiny piece. Right? That little tiny piece of the surface here. Remember, this is just a tiny patch of the bigger surface. So, yep, you take f dot n, that's the dot product, right? And so what are we measuring, right? We're measuring how much the vector field is flowing outward. If the vector field happens to be tangent to the surface, then it's orthogonal to n, and then the dot product would be 0, indicating that there's no flow through the surface. It's just going around the surface, but not through it. Okay? So yeah, at least in this example here, the vector has, some component pointing outward. So take the dot product and you get sort of this component of it as a scalar that flows outward. Right? The rest of it flows tangent to the surface, and we can ignore that part of it. Right? So that's what the dot product does, effectively. Right? And then you just add up all those patches. Right? This is an integral, so you do the integral over the entire surface here. And when you do that, you get this value. So this is the flux for this particular vector field over this particular surface, the cylinder, the parabolic cylinder. Right? Okay, then. That's our first example. Maybe we'll do one more. Okay, last one. Right, so I lost count. I think this is example 4, right? We did 2 surface integrals and then 1 flux integral, so this will be the second flux integral. So we're given the vector field, right? YZZ, so YI plus ZJ plus ZK, right? Yeah, unusual field, right? It looks like it should be XI plus YZ plus YJ plus ZK. That would be the outward vector. So this is not quite that. This makes it a little bit more complicated, right? And the surface is just the sphere of radius 4. So imagine this is the sphere, and this is 4 units long, right? So the sphere of radius 4. So what's different about this example is that this is a closed surface, right? The example we did, the previous example we did was an open surface, right? The mailbox, or the mailbox, but without a floor, right? No floor here. So this is an open surface, right? The sphere is a closed surface. I mean, as a practical matter, that's not going to make a whole lot of difference when calculating the flux integral, but it will make some difference later on, right? And just as a note, a lot of books, not ours of course, but a lot of books, when they write down the surface integral for a closed surface, and they want to emphasize that it's a closed surface, they will put a little loop through the two integrals. Our book doesn't do that, right? And in fact, this is comparable to a line integral. We did line integrals, but these were not normal vectors. These are tangent vectors over a curve, right? So if your curve was like this, it's an open curve, then we calculate the line integral, right? We know how to do that. Oops. But if it's a closed curve, like a circle, then some books would put a little circle through the integral, indicating that it's a closed curve. All right, I mean, you know, just letting you know that when you see that in other books, usually physics books, that's all it means, right? So here it's just the context of it, right? S is the sphere, oops, I want to cross it out. S is the sphere of radius 4, which is naturally a closed surface. So if you want to put a loop through there, fine. I'm not going to do it because our book doesn't do it either. So, all right. So yeah, so we have two ways of doing this, right? We can think of this sphere as a function plus or minus the square root of 16 minus x squared minus y squared. But I don't want to deal with the plus or minus. I mean, effectively, you just do the top half, and then by symmetry, you double it and do the bottom half. I think there's a symmetry here. I'm not sure. I'm not sure actually. But even if that's the case, I don't want to bother with the plus or minus square root, right? So I'd rather treat the surface parametrically, right, using u and v, right? So we did this already. I will remind you of the parameterization of the sphere, right, of radius 4. So now r is 4. So let's pull out the r. In this case, it's the 4. So x is going to be cosine u. No, I keep getting it wrong. Sine u cosine v, and then sine u sine v, and then cosine of u, right? And we already did the partial derivatives, so here they are yet again. So I pulled out the 4. So yeah, cosine u, cosine v, cosine u, sine v, and negative sine of u. And then the v partial of r is going to be 4 times negative sine u sine v, sine u cosine v, and then 0. And then we might need the cross product. We did that several times already. So when you do the cross product, don't forget you're multiplying 4 times 4, so you get 16 here. And then the vector will just be the usual sine squared u cosine v, sine squared u sine of v, and then it's sine u cosine u. Yep, right, because you're going to get cosine squared v plus sine squared v is 1. Right. Yeah, now, and we did the magnitude already. Just to remind you, the magnitude is going to be 16, that's the r squared, times sine of u. Yep. So 16 times sine of u. But we really don't need this here because remember we're doing the flux integral. And to do the flux integral, you just take f dot the vector ru cross rv without the magnitude, right? dA. Right. So let's do that. So this is the vector field. The vector field has components y, z, z. And then the dot product with ru cross rv. I can pull the 16 outside. This is going to be, well, let me just copy this down, right? Let's save some time here. There we go, right? And then dA, of course, is just, well, du dv or dv du. We should do u first. If you do dv du, then I think that usually reverses it, right? You get a negative, I think, in some cases. But I'm not sure about this one, right? So yeah, what is u? U is doing what here? U is phi, right? So u runs from 0 to pi, and v runs from 0 to 2 pi. Right? So u is the polar angle, v is the azimuthal angle, azimuthal angle. I think that's what it's called. In any event, right, yeah, it's the azimuth that runs around the equator, right? That angle there. Okay, so we take the dot product, but notice this is not going to work out because y, z, and z are not compatible with u and v. So what's y and z? Well, right, here's y, and here's z. So we should, before we take the dot product, maybe we should replace those. Oh, I didn't put the limits here, but I was going to do that later. 0 to pi, 0 to 2 pi, right? Okay, so now y is cosine of u. Z is, oh, no, I'm getting it backwards. Right, y is sine u sine v. Sine u times sine v. Z is just cosine of u. So this is also cosine of u. And then, well, can I just copy this down again? Oh, I bet I'm going to run out of space, so let me squeeze it in here. Sine of v. And then sine u cosine u, right? I think that's it. Du dv. Sine u cosine u. Yeah, just making sure. Okay. Now we can take the dot product, and yeah, you guessed it. It's going to be a horrible mess here. And I'm going to try to squeeze it in. So I'm going to write a little small. Apologies in advance. So this times this gives us sine cubed of u times sine v cosine v plus, remember it's the dot product, right? Cosine u times sine squared of u. So I'll do the sine squared first and the cosine of u, and then the sine of v, plus, and then cosine of u times cosine u sine u. So sine u and then cosine squared of u. And I think that's it, right? Oh boy. So what can we possibly do with this? Not much. I think we can factor out a sine of u, but that's the only thing these have in common. And that does not help at all, because that still has 3 terms. Yep, here you get 3 terms, sine u, cosine u, sine v. And then this is just cosine squared of u. Okay, so at this point, I don't think there's any hope of doing this by hand. Right. So this is where you're going to use a computer algebra system. Just plug it into your favorite MATLAB, Python. Well, Python's a programming language. Of course, you can program this in, but I was thinking either MATLAB or Mathematica. Those are the most common ones. Maple is kind of an older one, and some of them are very expensive. But Wolfram Alpha is the free version, and I think it will do this. So if you give me 1 minute, I will just plug this into Wolfram Alpha without the 16. We'll multiply by 16 later. Okay, it works, right? Yeah, so Wolfram Alpha will do double integrals. It will do this. And it gives me a rather nice answer. It's 4 pi over 3. Right? And you might think, well, isn't that just the volume of a sphere? Yeah, but it's not radius 4, right? It's the volume of a sphere of radius 1. So that's a coincidence, right? So 4 pi over 3. And so 16 times 4 is 64. So 64 pi over 3 is, I think, our final answer. And I just realized this is not correct. Oh. Okay. Probably a small mistake somewhere. Let me see. I'm sure some of you already know what it is. Hang on. It's a factor of 4. Of course. So, right. Yeah, y is not sine u sine v. I forgot the 4 on the outside. That's the problem with doing that here. So y is 4 times sine u sine v, and z is going to be 4 times cosine of u. So, yep, so my mistake was going from here to here. There should be a 4 here, a 4 here, and a 4 here, which means we can factor out that 4 from all three of these, and that multiplies 16. So this 16 at this point should have been a 64. Right, which means this should have been a 64, which means this should have been a 64. And now 64 times 4 is 256. So, okay, so the final answer should be 256 times pi over 3. Yep. Okay, yeah, I missed the 4, and that was bad. So I never should have taken it out. I should have left the 4 here. It does get to be kind of irritating when you're carrying around all these 4s and 16s and 64s. So I tend to, factor them out. And when I say factor them out, I hope you realize what I mean. I don't mean like, you're factoring out of terms here. When you have the vector, 4, 4, 4, you can write that as 4 times the vector 1, 1, 1. It's just scalar multiplication, right? So yeah, factoring it out is not the right term for it. I'm being not very precise about that. I'm just taking out dividing each component by 4 and then multiplying each component by 4 in the end. Okay, but that is the answer, 256 pi over 3. Again, that's the flux integral over the sphere. So the way to interpret this is we have your sphere of radius 4, and we have a vector field in space, right? It doesn't have to be radial. It could be this way, right? I'm not going to try to graph it, but on the surface of the sphere, you have, vectors pointing in various directions, all varying magnitudes too, I imagine. Right? It should be continuous, right? Right? And not just on the, outside, but, here as well. So I don't mean inside the sphere. I mean on the surface of the sphere. Right? So all these vectors are pointing in some direction over the surface of the sphere. And if you take a little piece of the sphere, say here, and blow it up, you get your vector field F on that piece, and then you get your normal vector n. Take the dot product, so cosine of theta, and you get the component, right, in this direction here, right, normal to the vector. Oh, it's probably this way. So it's going to be very short here, since it's pointing mostly tangent to the surface, but a little bit outward, a little bit normal to the surface. So yeah, that piece of it, the dot product will be very small over that piece of it. But again, you're adding up all those little pieces, and the total flux for the whole sphere is this number here, 256 pi over 3. Okay. So yes. So what saved us a lot of work was trying to calculate this double integral by hand, and I wouldn't even dare try. This is why we have computers and calculators. So, but yeah, maybe there's a way to do it by hand, but it's pretty awful. And it probably involves splitting this up into 3 separate integrals, and each one of those integrals is probably not that simple. It probably involves some sort of a reduction formula or substitution or something, I don't know. But it's not pleasant. So, yep, I took a little shortcut calculating the integral like this. So a better question would be, say, set up the double integral to calculate the flux integral, right, as a double integral, or right, as an iterated integral, right? In other words, you would basically leave your answer like this and not worry about evaluating it. So on a test, of course, I might not even ask you to evaluate it, as long as you can set it up correctly. Obviously, if you miss a factor of 4, you'll get a point off. So -1 for me. I got a point off for getting the wrong component, and probably a point off for getting the wrong answer too. So 2 points off for me. All right. Yeah, we're going to come back to this example again, right? But I wanted to do it directly this way, which is, it's a chore, right? It's a long problem here, and I even took a shortcut to do the integrals, and I got the answer just using a computer algebra system, right? So yeah, what I'm insinuating here is that there will be a shortcut to this, a shortcut that makes this calculation much easier. In fact, it probably just takes up 2 lines instead of what's about a dozen. So yeah, but that's coming in the next section. So this will be an example that we will do again. We will revisit this example and see how much easier it can be once we know the property, the theorem that establishes the relationship between these and what are going to be volume integrals. So we'll do a volume integral of some quantity that's going to be over the ball, which includes inside the sphere. Right. The surface integral just involves the surface of the sphere, not what's inside the sphere. Right. Okay. So that's surface integrals and flux integrals. I hope that helps.